are flexible. The bonds connecting the atoms, they stretch and they bend and they wobble. And the energy changes that correspond to all these movements match the energy of infrared light. So if you take a molecule and you irradiate it with infrared light of the correct frequency, then it will start to vibrate. And it's monitoring the absorbance of infrared light that is the basis of infrared spectroscopy. Now, if we take a simple molecule where you have two atoms connected together by a bond, this behaves very much like the classical simple harmonic oscillator. And the frequency with which that molecule will vibrate, the bond will stretch backwards and forwards, depends on two things. It depends on the masses of the atoms involved, and it depends on the stiffness of the bond. Now, chemical bonds in organic molecules come in three types.
So இதான் வந்து நம்ம root of k by nu அப்படின்னு சொன்னோம். Nuன்றது mass, kன்றது வந்து stiffness.
Single bonds, double bonds, and triple bonds. Single bonds are less stiff than double bonds, and triple bonds are the most stiff of all. So we can use these very simple concepts to look at where in the infrared part of the spectrum different molecules or different parts of molecules will absorb infrared light. So this is the infrared part of the spectrum. For historical reasons, chemists use a very odd unit to measure the frequency of infrared light. They use the inverse wave number, centimeters to the -1. And the infrared spectra of organic compounds are typically recorded in the range of 600 to 4,000 wave numbers, inverse centimeters. Now, when we look at the left-hand part of the chart, we can start to group together particular types of bonds. For instance, oxygen to hydrogen bonds, nitrogen.
See here, that's what I discussed with the example. The same example we will also discuss. 4,000 to 1,500. It is characteristic of individual groups. 1,500 less than 1,500, it is a function of the individual elements. We'll see that.
Hydrogen bonds and carbon to hydrogen bonds are all on the far left hand side, and you can see a small difference between the OH, NH and the CH bonds. These are all in that particular position because they all involve the lightest atom, which is the hydrogen atom. The stiffest bonds, that is the triple bonds, and whether they're triple bonds between carbons or nitrogens or oxygens, they're all in roughly the same place, and that's at approximately 2,000 wave numbers. Not quite so stiff are the double bonds, carbon-oxygen double bonds, carbon-carbon double bonds, carbon-nitrogen double bonds, and these are all grouped around 1,600 to 1,800 wave numbers. You'll notice that all of these are in the left-hand part of the spectrum. They're all above 1,500 wave numbers. This region of the spectrum is characteristic of the class of compounds.
Class of compounds na group identify பண்றதுக்கு என்ன group அதில் இருக்கு அப்படின்னு சொல்லலாம். That is what meant by class of compounds. Whether it's a nitrile group, இல்லை alkene group, இல்லை carboxyl group, என்ன group identify பண்றதுக்கு.
So if you look at the information from the part of the spectrum above 1,500 wave numbers, it tells you about the class of compounds to which your sample belongs. It's not very helpful at telling you which specific compound in that class your sample is. So above 1,500 wave numbers, it's a very useful region for research chemists. But it's not a very useful region for forensic scientists, because forensic scientists want to individualize their compound down to one particular one. That is best done on the right hand half of the
ஓகே என்ன சொல்கிறாங்கன்னா ஸோ ஃபாரன்சிக் சயின்ஸில் வந்து இப்போ ஒரு காம்பவுண்ட் இருக்கா இல்லையான்னு கண்டுபிடிக்கும் போது ஜஸ்ட்டு வந்து அதில் கார்போக்சைல் குரூப் இருக்குது நைட்ரைல் குரூப் இருக்குதுன்னு மட்டும் இன்ஃபர்மேஷன் தெரிஞ்சால் போதாது எக்ஸாக்டாக என்ன காம்பவுண்ட் இருக்குன்னு தெரிஞ்சால் தான் வில் பி ஏபிள் டு டேக் ஸ்டெப்ஸ் ஸோ அதான் சொல்கிறாரு greater than 1500 வந்து it will be very useful for research chemist ஸோ ஒரு என்ன காம்போனண்ட் ஃபண்டமெண்டலாக இருக்குது அப்படின்னு தெரிஞ்சுக்கலாம் பட் அப்ளிகேஷன் பாயிண்ட் ஆஃப் வியூவில் ஃபொரன்சிக் சயின்டிஸ்ட்க்கு எந்த ரீஜன் ரொம்ப யூஸ்ஃபுல்லானா ஃபிங்கர் பிரிண்ட் ரீஜன் தான்
spectrum below 1500 wave numbers. In this part of the spectrum you have all the single bond vibrations. You have all sorts of bending modes. You also have all sorts of complex deformations. It's a very complex part of the spectrum. But this means that the spectrum you record below 1500 wave numbers is characteristic of a specific compound. In fact, this part of the spectrum acts very much like a molecular fingerprint. So if you take the infrared spectrum of your unknown compound and you look in this region and you compare it to the standard sample, the infrared spectrum of the standard sample, and those two match, then you've got a very strong identification of that compound. Here's an example.
This is what I actually used.
It's an infrared spectrum of diamorphine, which is the active ingredient of heroin. And if we look on the left-hand half of the spectrum, which is outlined in red, you can see a series of bands. And if you look closely at that part on the left-hand side, it tells you about some of the parts of the molecule. For instance, we can see that this molecule has ester groups. We can see that it has carbon-hydrogen bonds. But there's nothing in the left-hand half of the spectrum that tells us this is diamorphine. It simply says this has some of the chemical functional groups that diamorphine also has. It's only when we look at the right-hand half of the spectrum outlined in blue, the so-called fingerprint region, that we can say this is diamorphine. It's, as you can see, it's very complex, it's very rich in detail, and comparison to an authentic sample proves that this is indeed diamorphine.
Fine. So that tells you what is the importance of this IR spectrum. We'll come back. I'll just present you the entire screen now. Able to see the blackboard?
Yes, sir.
Thank you. Okay, so last class morning we saw the different types of radiation sources for IR, and we started the sampling methods. So what I mean by sampling is, so நம்ம ஒரு particular sample எடுத்து அந்த sample வழியாக IR பாஸ் பண்ணி எப்படி IR ஸ்பெக்ட்ரம் வருது அப்படின்றத பார்க்கணும். அப்போ இந்த சாம்பிளுக்கான தன்மைகள் என்ன மாதிரி சாம்பிள் இருக்கணும், சாம்பிள் எப்படி ஹேண்டில் பண்ணுறது. ஓகே, எல்லா அனலிட்டிக்கல் இன்ஸ்ட்ருமெண்ட்டுமே சாம்பிள் ஹேண்ட்லிங்கிறது ஒரு செப்பரேட் ஏரியா. ஹவு டு ஹேண்டில் த சாம்பிள் அப்படின்னா என்ன சால்வெண்ட் யூஸ் பண்ணணும், சாம்பிள் ஹேண்ட்லிங்னா என்ன அர்த்தம் அப்படின்னா என்ன சால்வெண்ட் யூஸ் பண்ணணும், எந்த ஃபார்மில் சாம்பிள் இருக்கணும், லிக்விட் ஃபார்மில் இருக்கணுமா, லிக்விட் கேஸ் ஃபார்மில் இருக்கணுமா, என்ன ஃபார்மில் இருக்கணும்னு சொல்கிறது. அண்ட் மார்னிங் ஐ டிஸ்கஸ்ட் யூ அண்ட் டோல்ட் யூ தட் most of the elements are not transparent to IR. So the most commonly used for IR is sodium chloride அல்லது potassium bromide யூஸ் பண்ணுவாங்க. அதுலேயும் sodium chloride வந்து 4000லேருந்து 650 per centimeter ரேஞ்சில், less than 650 per centimeter ரேஞ்சில் potassium bromide யூஸ் பண்ணணும்னு சொல்லியாச்சு. இப்போ நம்ம இண்டிவிஜுவலாக ஒரு சாம்பிளும் எப்படி ப்ரிப்பேர் பண்ணுறதுன்னு பார்ப்போம். ஃபஸ்ட்டு வந்து கேஸ், how to prepare gas samples. So as far as gas sample is concerned, okay, so in the gas sampleக்கான கண்டெய்னர் இப்படி தான் இருக்கும். Okay, this is your chamber. You can see this window. Just take a red color. Okay, so this particular window is nothing but, or see here also, this window is made up of either sodium chloride or potassium bromide. This window is either made up of sodium chloride or potassium bromide. So this is your sample. So sample gaseous state la irundhalum adhigama solvent mix panna matanga. They will also mix with some amount of potassium bromide and they will place inside this chamber. Vachittu இந்த gas இந்த chamberல இருக்கும். On either side there will be a window. So through that window only your IR will be passing. Okay, this is as far as gas is concerned. So sample kuda solvent normally idhu mix panna matanga. So sample or container la vechiruvaanga. And the container oda window, வந்து it is made up of either sodium chloride or potassium bromide இருக்கு. இது வழியா உங்களுடைய IR radiation பாஸ் பண்ணுவாங்க. So this is for gases. Okay, so this is two types of construction. This is a circular kind of convention, this is a square type of convention. The second type, this is particularly for liquids and solids. First we'll see for liquids. For liquids, this is the technique that is followed. See, என்ன பண்ணுவாங்கன்னா ஒரு plate எடுத்துப்பாங்க. Just use a white color. Okay, they'll take a plate. Idhula they will use one drop of the sample and they will also mix sample kuda, they will mix it with nujol. Nujol is a mineral oil. It is hexachloro butadiene. That is a chemical composition of nujol. Hexachlorobutadiene. It's a mineral oil. They call it as nujol. Okay, so this sample is mixed with nujol. Mix பண்ணி ஒரு paste மாதிரி ஆக்கிடுவாங்க. It will be made into a paste. Okay, it will be made into a paste. This will be made into a paste. In the paste ஒரு பிளேட்ல they will have a drop of that paste. This is that one. இந்த இடத்துல காட்டுறாங்க இல்லைங்களா, this part இந்த பிளேட்ல கொடுத்துருக்கிற ஒரு drop. This is actually the sample mixed with nujol. ஒரு paste மாதிரி ஆக்கிறாங்க. ஆயில்ல மிக்ஸ் பண்ணா என்ன ஆகும், பிசுப்பா ஒரு பேஸ்ட் மாதிரி ஆகுதுல்ல, அதான் இது இங்கே வச்சிடுறாங்க. வச்சுட்டு on either side you are closing it with potassium bromide windows. Okay, so these are all, இது ரெண்டும் என்னன்னா sodium chloride அல்லது potassium bromide window. இப்போ இது மூணுமே ஒரு something like a sandwich. ஓகே, உங்கள் சாண்ட்விச்சில் நடுவில் வெஜ் அண்ட் சிக்கன் பீஸ் இருக்க மாதிரி நடுவில் வந்து இந்த பிளேட்டில் மினரல் ஆயில் இருக்கும். மினரல் ஆயில் சாம்பிள் கூட மிக்ஸ் பண்ணது. ஆன் எய்தர் சைட் யூ ஹேவ் அ பிளேட் ஆஃப் பிரெட் மாதிரி வச்சுங்க. இட்ஸ் லைக் யுவர் பிரெட் மாதிரி யூ ஹேவ் யுவர் சோடியம் குளோரைட் ஆர் யுவர் பொட்டாசியம் புரோமைட். எய்தர் சோடியம் குளோரைட் ஆர் பொட்டாசியம் புரோமைட், எனி ஒன் இட் இஸ் ஆட். ஸோ இது மூணுத்தையும் ஒன்றா சேர்த்து it will be kept in the path of the light. Okay, this is for liquids. Liquid என்ன பண்ணுவாங்க, sample கூட they will mix it with nujol and they will make it as a paste, give on a or plate la vachi it will be sandwiched by two sodium chloride plates or two potassium bromide plates, and this arrangement of sandwich is kept in the path of the light. Okay, and the third is for solids. For solids, the technique is called as pellet technique. Pelleting. What is a pellet? Anyone tell what is a pellet?
Sir, it's a bullet, sir. It's compared to a bullet.
Bullet, na?
It's a prototype of bullet, sir.
Bullet na enna artham?
bullet sir.
புல்லட்லாம் இல்லை, இது பேர் பெல்லட் தான். ஓகே, பிஇ
டேப்லெட்
டேப்லெட், கரெக்ட். பெல்லட்ன்றது டேப்லெட் மாதிரி. பெல்லட் இஸ் சம்திங் லைக் ஏ டேப்லெட். ஓகே, ஸோ இதில் என்ன பண்ணுவாங்கன்னா, சே 1 கிராம் ஆஃப் சாம்பிளுக்கு 100 grams ஆஃப் கேபிஆர், இது ரெண்டுத்தையும் மிக்ஸ் பண்ணி நல்லா பவுட்ரு வச்சு நல்லா மிக்ஸ் பண்ணிவிடுவாங்க. நம்ம இது குட்டி உரல் இது வச்சு மிக்ஸ் பண்ணுவோம்ல, அந்த மாதிரி நல்லா மிக்ஸ் பண்ணிவிட்டு இதை ஒரு இந்த மாதிரி கேஸ்டிங் டையில் வச்சுருவாங்க. ஸோ இந்த கேஸ்டிங் டைக்குள்ளே வச்சு they will press it so it will convert into a tablet. It will become a tablet. Okay, this will be kept in the path of the IR. Okay, so 1 gram of sample kuda 100 gram of KBR is mixed and ஒரு டை கேஸ்டில் வச்சு அதை ப்ரெஸ் பண்ணி அதை சின்ன சின்ன டேப்லெட் ஆக்கிடுவாங்க. ஸோ திஸ் வில் பி கெப்ட் இன் த பாத் ஆஃப் த லைட். This will be kept in the path of the light. Okay, so that's how you handle solid samples. We'll see how this is done now. Okay, you can see here. Let's put it. முதல்ல இப்போ சாலிட் சாம்பிள் பண்ணுறது காட்டாங்க.
Once you get the 100 milligrams, then place the measured potassium bromide off to the side. Next, zero the balance again with a new wayboat.
ஸோ ரெண்டுமே எடுத்துப்பாங்க, ரெண்டு சாம்பிள் எடுத்துப்பாங்க, மிக்ஸ் பண்ணுவாங்க ரெண்டுத்தையும். இப்போ
measure out 0.1 and record the weight.
Weight check பண்ணிக்கிறாங்க 1 to 100.
Ideally, a smaller amount of the sample is best. Set your sample to the side with your measured amount.
Okay, now it is just poured into that.
Combine the measured amounts of potassium bromide and the sample into the mortar. Use the pestle to grind the two solids together. Do this for about 20 seconds so that both solids are mixed evenly and ground well.
This is your pellet.
Next,
Okay.
to prepare the bolt, screw in the bottom screw, being careful not to over-tighten. Transfer your sample from the mortar to a third unused wayboat and then into the open end of the bolt. Secure the top with a second screw.
So it is sent into that particular thing. We're actually showing the pelleting technique. So இதை வந்து ஒரு இதில் வச்சு they will tighten it.
Move the bolt to the clamp and secure in position. Using a torque wrench, tighten the top bolt until you hear a click and the wrench goes no further. Set a timer for 1 minute and let the bolt sit until the timer expires. Rotate the top of the torque wrench in the meantime so you can unscrew the bolt later. Place back on the screw and bolt and push until the bolt releases.
Okay.
Tap the sides of the bolt on the lab bench to remove loose particles.
So this
Turn
is
the IR
placed
on and
into
make sure
the
background scan has been run without the bolt.
அந்த நடுவில் இருக்கிறது ஆக்சுவலாக உங்களுடைய சாம்பிள் which is in the form of a pellet. அந்த pellet டைரெக்டாக வெளில எடுக்க மாட்டாங்க, இந்த அரேஞ்ச்மெண்ட்டோடவே அதில் வச்சிடுறாங்க. ஸோ this light கரெக்டாக அந்த radiation will be passing through the center of it.
Bolt in the machine and then hit scan.
This is a IR
Your
spectrometer.
spectrum will be produced.
Liquid சாம்பிளுக்கு
Luckily, liquid sample prep is much easier. To prepare a liquid sample, take the salt plates from the desiccator. Then rub the salt plates on the surface to clean them. Once cleaned and dried, place a drop of your sample on one of the salt plates. Place the other and make sure that a background scan has been run containing the drop. Walk over to the IR and make sure that a background scan has been run.
Okay, I'll just tell you one thing.
Your sample so that the beam is able to pass through it. You are now ready to scan. Your spectrum will be produced by the machine.
And rub again on the surface. Do not wash. To clean up from a solid sample.
Okay, actually first for recording they will take only the empty one, okay, empty one without the sample. They will get an output. Then they will take with the sample. So the background noises will be eliminated for that purpose. That acts as like a reference. They'll use only the without pellet, okay, without the actual sample. You keep only the sodium chloride, potassium bromide window mattum vachi. They will take a spectrum first, then they will use along with your sample, and the background will get cancelled out. Okay, that's how it will be done. So we'll come back. Okay, so from this we'll move on to the types of detectors. So we have seen about what are the sources, what are the types of how the sample is prepared. Next we'll concentrate on detectors. Already we have seen the detectors in the morning. Many of you have given the things, okay. So since it is heat, we have to measure. We have different kinds of temperature measuring devices. The first one in the line is you can use a thermocouple. Already you know what is a thermocouple and other things. Second one, you can use a bolometer. Bolometer is something like your RTD or your it's almost like an RTD. Either you have a platinum or nichrome strips. Platinum or nichrome strip. This is the thing. This is how a bolometer looks like. Okay. So this is the surface where, see, it shows here. This is the absorbing layer for the infrared radiation. So it will absorb the infrared radiation. Thereby, when it absorbs the infrared radiation, its resistance actually changes. Its resistance changes. Thereby, you can measure that resistance change. Okay, that's how your bolometer works. The third kind of detector is what Balamurugan has put the diagram. No, many students have used it. Pyroelectric detectors. Pyroelectric detectors. Simple terms, if you tell pyroelectric detectors, they are nothing but temperature dependent capacitors. Temperature dependent capacitor, that's called as pyro detector. Temperature dependent thing. Okay, here you can see, just use pen. Okay, here you can see this is your pyroelectric. This is how your pyroelectric detector looks on the top, and this is a cut section view of your pyroelectric detector. This is a cap. This part, this blue part is a cap which has an infrared broadband filter. This is allowing only infrared light to pass through it. Inside, see, this is the actual pyroelectric element. This is the actual pyroelectric element. Okay, so this element, okay, it's called triglycerine sulfate. Triglycerine sulfate is a material. Okay, so TGS, they normally call it as TGS, triglycerine sulfate. Triglycerine sulfate. Okay, so that's the element that is available here. So what happens when the infrared light flows through this particular glass into the infrared? The infrared basically it's heat radiation, right? So this particular black body, it's almost like a black body, right? It absorbs the infrared. It absorbs the infrared radiation. Because of this absorption of infrared, the charges rises. Its charge rises. On the surface, charges rise. Surface charges rises. So internally, on the back side of it, there will be a JFET or an op amp, which will convert this charge into an voltage. This charge developed due to the absorption infrared will be converted into an voltage. So that is how you will be having your pyroelectric detector. Okay. So this is again detector for heat. It absorbs the heat, changes the charges. So when it charges changes, nothing but you can simply say its capacitance is going to change. And charge distribution changes, it actually works as a parallel plate capacitor. When its charge distribution changes, your capacitance is going to change. When its capacitance change, you can measure what is the voltage. That's why it's called as temperature dependent capacitor. This is how your pyroelectric detector works. This is TGS. And the last class of detectors are called photodetectors. Photodetectors. So here you have mercury sulfate. Mercury sulfate is the element. Okay. So this is this is how your photodetectors use. So it absorbs your infrared. Okay, it absorbs your infrared. It converts the light into all simply I can put it is equivalent to that of your PMT. It is equivalent to that of your PMT in your UV visible spectroscopy. UV visible PMT enna work pannudho adha idu pannudhu. Light vaangi light amplify panni veliye kudukum. That is a photo detector. So inga heat varudhu, heat vandu light ah maathum. Mercury sulfate enna pannuna, it will convert your heat into light. Light photons ah varum. And the light photons PMT mariye ulla irukka diodes moolama amplify panni you will get an output, electrical output. It's very much equivalent to that of your PMT in your UV visible spectroscopy. Okay, that's called as photodetector. It is made up of mercury sulfate. Okay, so these are the different kinds of detectors. So we have seen what are the sources. Okay, what are the sources? So sources la enna paathom, nurse glare, glow bar, nichrome wire, carbon dioxide laser. Then we have seen modulators. What I mean by modulator is sample handling. What I meant is sample handling. So not modulators. Okay. So it is sample handling. So it is sample handling we have seen. Then we have seen detectors. Okay. Now we'll see the complete block diagram. Okay. So again you can use modulator use பண்ணுவாங்க, grating வரும். You have grating here that will be used. Okay, but all grating we have seen already. I'm not going to touch upon that. So now when you consider the instrument, okay, when you consider instrument, full region cover பண்ற மாதிரி single instrument வராது. Okay, so this is your ranges. Again I will redefining the ranges. So you have near infrared region. I'll just use red pen. Okay, here you have near infrared, mid infrared and the far infrared. Okay, can see the range I have given in both micrometers and per centimeter. In micrometer range it is 8 to 2.5, it is near. 2.5 to 50 is mid, 50 to 1000 is far. Or you can take it in terms of per centimeter, 12,500 to 4,000 it is near infrared, 4,000 to 200 it is infrared, mid infrared, 2,000 to 10 it is far infrared. நமக்கு வேண்டியது முக்காவாசியான எல்லா அனாலிசிஸுமே 4,000 to 200 குள்ளரே வரும். this is a range. Most of the analysis application wise பார்க்கும்போது infrared spectroscopy ல absorb பண்ற species வந்து will have its application, whether it's pharmaceuticals or forensics. Okay, it will be coming in the mid region only. Okay, mostly mid region is most commonly used. Okay, fine. So near infrared la konjam wavelength it is possible to see with naked eye. It's possible to see with naked eye. Fine. So coming to the instruments, complete instrument, we have three classes of instrument, or three types, two types. As per your syllabus it is two types. First one is dispersive IR spectrometer. Dispersive IR spectrometer. Second one is FTIR spectrometer. FTIR spectrometer. Okay, and the recent one that is available in market is ATR spectrometer. I'll just touch upon the spectrometer at the last. This one is the latest. These two are latest. Modern instruments include FTIR as well as ATR. Even in IIT Madras they will have ATR type of spectrometer. Both they will have. Okay, we'll touch upon these two last. Okay, first we'll see what is a dispersive IR spectrometer. From your diagram you can see it is almost resembling to your UV visible spectrometer. It's almost like your double beam UV visible spectrometer. It's almost like a double beam UV visible spectrometer. Can you see any particular difference apart from your UV visible spectrometer? UV visible spectrometer la ஞாபகம் இருக்கா block diagram? So அந்த block diagramத்துக்கும் இதுக்கும் முக்கியமான ஒரு டிஃபரன்ஸ் இருக்கு. Can you spot it? இந்த படத்தை பாருங்க. இந்த படத்துல இருந்து can you spot the very important difference compared to your UV visible spectrometer and this IR? இல்லை. Okay, I'll just tell, mute yourself. Okay, see இதில் எங்கே இருக்குது பாருங்கள் சாம்பிள். நம்ம நார்மலாக யூவி விசிபிளில் முதல்ல சோர்ஸ் இருக்கும். சோர்ஸ்லேருந்து வர அவுட்புட்டை வேவ்லென்த் செலக்டரை வச்சு செலக்ட் பண்ணுவோம். அதுக்கப்புறம் தான் அந்த லைட்டை சாம்பிள் வழியாக பாஸ் பண்ணுவோம். த சாம்பிள் வில் கம் ஆஃப்டர் த வேவ்லென்த் செலக்டர். இங்கே எங்கே இருக்குது பாருங்கள் சாம்பிள். த சாம்பிள் இஸ் கம்மிங் பிஃபோர் த டிஸ்கிரிமினேட்டர். டிஸ்கிரிமினேட்டரோட பர்பஸ் வந்து ரெக்கார்டிங்கு போகிறதுக்காக மட்டும்தான். Here the discriminator role is sending the output to your recording. The discriminator role is sending the output to the recorder. உங்களுடைய மெயின் ஒர்க் சாம்பிள் வழியாக பாஸ் ஆகிற ரேடியேஷன் டைரெக்டாக பாஸ் ஆகுது பாருங்கள். The sample comes in between your source and monochromator. உங்களுடைய UV visible in your UV visible you add the source, you add the wavelength selector, that is your monochromator, then you add your sample. In your IR your sample comes in between your source and monochromatic radiation. Okay, that's it. Okay, so light source ஃபுல்லாகவே டேரெக்டாக சாம்பிள் வழியாகவும் ரெஃபரன்ஸ் வழியாகவும் பாஸ் பண்ணுறோம். அதுலேருந்து வர அவுட்புட்டை மட்டும் தனித்தனி வேவ்லென்த்தாக ரெக்கார்ட் பண்ணுறதுக்கு மட்டும்தான் வந்து we are using monochromator. Otherwise monochromator role is not used here. Okay, so sample directa or light source directly you are sending it to the sample, then only you are using the monochromator. It's a fundamental difference between your double beam UV visible spectrometer and your dispersive type IR spectrometer. That's the very very important difference. Okay, so I'll just show you an IR spectrometer so that you can understand better. Not this one. Okay, see this video. This will tell you about the full IR spectrometer. With this we'll actually close the class. Time ஆயிடுச்சா? ரொம்ப டைம் ஆயிடுச்சா? இல்லை இன்னும் 6 நிமிஷம் இருக்குது. கரெக்டாக 6 நிமிஷம் இந்த வீடியோ இருக்குது.
Infrared spectrometry helps chemists to identify the functional.
ஆடியோ வருதுல?
இல்ல சார்,
கேட்கல?
கேட்கல சார்.
Just a minute. இப்போ
groups present in a compound.
கேக்குதா?
கேக்குது சார்.
Okay, okay.
Yes sir.
The structure of a compound. A pair of atoms joined by a covalent bond can be thought of as being like balls on the end of a vibrating spring. The bond can vibrate with different amounts of energy at a frequency that depends on the masses of the atoms and the strength of the bond. Lighter atoms give higher frequencies. Heavier atoms move more slowly and so give lower frequencies. Stronger bonds give higher frequencies, and weaker bonds lower ones. At room temperature, most bonds will vibrate with the lowest possible amount of energy. But if radiation of the right frequency is supplied, the bond can absorb energy and vibrate with greater amplitude. Most bonds absorb energy in the infrared region of the electromagnetic spectrum, which corresponds to heat. Each bond, such as OH, C double bond O, NH, and so on, absorbs at a particular frequency, and this allows it to be identified. For historical reasons, and because the numbers are easy to work with, chemists dealing with IR spectra use units called wave numbers, measured in centimeters to the -1, which are proportional to frequency.
Can see the cut section
All
of
IR instruments have a source of IR radiation.
okay, see the cut section of our IR spectrometer. You can see step by step. It will be very useful.
This is a coil of wire surrounded by a ceramic capsule, which is heated electrically so that it gives out IR radiation. In other words, heat over a whole range of frequencies. The IR radiation goes via a series of mirrors into the sample, which is placed here in an appropriate holder.
See,
The
directly the sample goes into the radiation IR input directly goes into the sample.
radiation not absorbed by the sample arrives at a detector situated here. Modern instruments, such as this one, use a device called an interferometer.
Okay, so இது வந்து FTIR ஸ்பெக்ட்ரோமீட்டர் ஆக்சுவலாக காட்டுறாங்க. அதில் வந்து இன்டர்ஃபெரோமீட்டர்னு ஒரு பார்ட் வரும். ஸோ நெக்ஸ்ட் கிளாஸ் நம்ம FTIR ஸ்பெக்ட்ரோமீட்டரும் அதில் இன்டர்ஃபெரோமீட்டர் பார்ட்ஸும் பார்ப்போம். இப்போதைக்கு வீடியோ பாருங்கள்.
Of a beam splitter here, and a pair of mirrors at right angles to one another. This produces what is called an interferogram from the source radiation. The interferogram holds information about the intensity of all infrared radiation at all frequencies simultaneously. This passes through the sample and to the detector. The interferogram that arrives at the detector can be decoded by a mathematical technique called a Fourier transformation. This gives the intensity of the infrared radiation at each frequency separately.
So actually that's the difference between your dispersive type and FTIR type. Dispersive typeல பின்னாடி நம்ம ஒரு கிரேட்டிங் வச்சுருக்கோம். அந்த கிரேட்டிங் வழியாக ஒரு வேவ் லென்த்தாக தனித்தனியாக ரெக்கார்ட் ஆகும். ஓகே, FTIR ஸ்பெக்ட்ரோமீட்டரில் எல்லா வேவ் லென்த்தும் ஒரே டைமில் ரெக்கார்ட் ஆகிடும். பிகாஸ் யூ டேக் த Fourier transform of the signal. Okay, that will actually reduce the time.
The transformation is handled by the computer and produces a graph of percentage transmission against wave number. This is what the chemist interprets. The essential point is that pulses of infrared radiation consisting of a range of frequencies simultaneously.
See here, this is 2000 actually, around 2000, less than 2000. This is indicating the compounds. என்ன class of compounds இருக்குன்னு சொல்கிறது. 2000 கம்மியாக இருக்கிறதெல்லாம் பாருங்கள் peaks எப்படி இருக்குன்னு. So this will be very complex, but it will indicate what is the actual individual compound.
Pass through the sample and arrive at the detector. Some frequencies are absorbed more than others, depending on what bonds are present in the sample. This is the sample holder. The sample is placed here on a crystal which is made of diamond or germanium. The
Okay, this is actually ATR kind of spectrometer. So ATR ன்றது என்னன்னா attenuated total reflection. நம்ம இதில் வந்து fiber opticல how the light is transmitted inside by a principle of total internal reflection. லைட்டை ஒரு பர்டிகுலர் ஆங்கிளில் உள்ளே விட்டோம்னா லைட்டு உள்ளார இன்டர்னலாக ரிஃப்ளெக்ட் ஆகி உங்களோட உள்ளே டிரான்ஸ்மிட் ஆகுது இல்லையா? ஸோ அதே பிரின்சிபிள் தான் இங்கே. இங்கே ஒரு கிறிஸ்டல் இருக்கும், அந்த கிறிஸ்டலுக்கு மேலே தான் உங்களுடைய சாம்பிளை வச்சுருப்போம். இப்போ என்ன பண்ணுவோன்னா இந்த கிறிஸ்டலுக்குள்ளார இந்த லைட்டை டைரக்ட் பண்ணுவோம். ஸோ உள்ளார போயிட்டு இன்டர்னலாக ரிஃப்ளெக்ட் ஆகும். ஸோ இன்டர்னலாக அந்த சர்ஃபேஸ் கூட இன்ட்ராக்ட் பண்ணிவிட்டு இட் வில் கம் பேக். ஸோ பை இன்டர்னல் ரிஃப்ளெக்ஷன் மூலமாக தான் இதில் வந்து ஐஆர் வந்து சாம்பிள் கூட இன்ட்ராக்ட் பண்ணும். via internal reflection it will interact with the sample. ஸோ இந்த ஏடிஆர் மெத்தடில் இருக்கக்கூடிய சாம்பிளுக்கு வந்து நம்ம எதுவுமே சாம்பிள் ப்ரிப்பரேஷனே எதுவுமே தேவையே இல்லை, பிகாஸ் இட் அண்டர்கோஸ் ஆல் த ப்ராசஸ். ஸோ இதில் வந்து சாம்பிள் ப்ரிப்பரேஷன் எதுவுமே தேவையில்லாமல் யூஸ் பண்ண முடியும் இந்த மெத்தடில். ஓகே, ஸோ ஏடிஆர் ஸ்பெக்ட்ரோமீட்டர் இது வந்து ஏடிஆர் பேஸ்ட்.
IR beam is directed into the sample by a mirror. It is reflected back from the upper surface of the sample before being guided into the detector by a second mirror. This method is called attenuated total reflection, or ATR. Here, we will run the IR spectrum of solid benzoic acid. The instrument is switched on, and a blank is run with no sample in place. This is to find the absorption of the air.
Okay, so that is to record the background noise. First they will record it without any sample,
Which must be subtracted from that of the sample. A little benzoic acid is placed on the ATR crystal. This is a holder for...
பாருங்க சாம்பிளை வந்து டைரெக்டாக இன்ட்ரடியூஸ் பண்ணுறாங்க. யூ டி நாட் டூ எனி பெல்லட்டிங்கோ இல்லை முஜால் டெக்னிக்கோ இல்லை விண்டோவில் வைக்கணுமோ எதுவுமே தேவைப்படாது. Directly you can use the sample for ATR.
Solid samples. Less than a milligram of solid sample is required. The torque wrench is used to squash the sample to ensure a good contact with the surface of the crystal. For most samples, no preparation is required. Details of the scan are entered into the computer. The spectrum of the sample is obtained within a few seconds. The wave numbers of the more significant peaks can be labelled onto the spectrum. This helps the chemist to interpret the data. This peak is caused by a stretching vibration of the C double bond O, and this by an OH stretch. These two peaks together suggest that the sample may have a carboxylic acid functional group which has both C double bond O and OH bonds. An unknown sample may be identified by matching its IR spectrum with a database of spectra of known compounds, particularly in the region of the spectrum below about 1500 centimeters to the -1. The peaks in this area are due to complex vibrations of the whole molecule, and the area is referred to as the fingerprint region because it is unique for a particular compound. For a liquid sample, the procedure is the same, but a few drops of liquid are placed in this type of sample holder. The cover is to prevent the evaporation of volatile liquid samples.
Okay, so that's how your IR spectrometers work. Okay, so in this